Okay, so we are going to resolve vectors today. So if we have some vector, if this is our x and y axis, we have some vector, we'll call it D. We'll put our little vector symbol over it. We have some vector D and it's at an angle of, let's say, 32 degrees, and we'll say that this is 5 meters. So the way we can write this is D is equal to 5 meters at 32 degrees. So it's hard in physics to work with a vector that's at an angle like this, so we have to do what's called resolve it into x and y components. So we are resolving into x and y components. Why are we going to want to do this? So in the future, when we start adding a lot of vectors together, or trying to find out what a certain force is going to do on something, it makes sense to resolve these components, because in physics and engineering, we can only deal in the x and y directions. We have a tough time dealing in diagonals. Okay, so I'm going to change my color here. So what we're going to do is we're going to drop down from the end of this vector right here, so that we're making a right triangle with the x-axis right here. So I'm going to pick a different color and make this pen a little bit thicker. So from here to here, starting at the x-axis, I can draw an arrow along the x-axis, and we can call that dx, because that's the projection of this vector d in the x direction. And change back to red here. So then drawing this line that we drew down right here, I'm going to draw an arrow here. This vector we're going to call dy. That is the component of the projection of vector d in the y direction. So this looks like those right triangles that we were talking about in the math skills section in Unit 1. So what can we do? How can we find the length of these two angles? Sorry, these two legs of the triangle. So change back to blue. So we're going to use this blue color for x. So this cosine 32, let's look at dx right here. So dx, this is adjacent to 32. We know the hypotenuse right here is 5 meters. So this d vector, that's like the hypotenuse. So if we think back to, remember, sine of an angle was opposite over hypotenuse. Cos was adjacent over hypotenuse. Tan was opposite over adjacent. I should probably make my line thickness smaller because we're running out of room. Okay, so which one are we going to use for dx? That's the adjacent angle. We know the hypotenuse. So we can say that cosine of 32 degrees is equal to dx over 5 meters. So we can solve that. So we can say component dx is equal to 5 meters times cos of 32 degrees. So if we work that out and plug that into our calculator, that turns out to be dx is equal to 4.24, and then we have to have our unit meters. That is the x component of this vector d. All right, we had red for dy. So now dy, this is the opposite side, so we're opposite to this 32 degree angle right here, and we have the hypotenuse. So we want to use sine. We could totally use tangent, but what if we had done this the cosine calculation wrong? So we're going to use sine of 32 is equal to dy over 5 meters. So dy is going to equal 5 meters times sine of 32. So dy, we plug that into our calculator, should get 2.65 meters. So I'm rounding to 3 sig figs, so use your sig figs rule. All right, so if we want to write this in I hat, j hat notations, the IJK notation, go back to my purple color. So we could totally write vector D. So remember we said our x direction was our I hat and our y direction was j hat. So if we're going to write it in IJK notation, we would write this as, that looks messy, 4.24 I hat plus 2.65 j hat. So now we've got another way to represent this same vector up here. So both of these vectors are equivalent. These are both vector D. We're just representing them in different notations. All right, and that's it for vector resolution. So next time we will talk about how we can use these to add different vectors together.